What does science say about time traveling? Time feels familiar because it is always present. It moves with us through every moment, quietly stitching one experience to the next, never pausing, never reversing, never seeming to offer a choice. We notice it most clearly when it slips away, when a memory feels distant, or when anticipation stretches the seconds thin. Yet beneath that everyday intimacy, time is one of the least understood elements of reality. Physics does not treat time as a simple background clock ticking for everyone in the same way. Instead, it treats time as something woven into the structure of the universe itself, something that can stretch, compress, and behave in ways that quietly challenge our instincts. The idea of traveling through time usually arrives from stories, from machines with dials and doors, from dramatic leaps into the past or the future. Science approaches the same idea from a much quieter direction. It begins by asking what time actually is, how it behaves under known physical laws, and whether those laws leave any room at all for movement through time that resembles travel. Before imagining destinations, physics first examines the road itself, because in science, possibility is determined not by desire but by structure. If you are enjoying this quiet exploration so far, you are welcome to gently like or subscribe, and you can share where you're listening from if you'd like. It helps keep these calm conversations unfolding. Physics begins its modern understanding of time with a realization that arrived in the early 20th century, when Albert Einstein noticed something unsettling about motion and light. No matter how fast an observer moves, light always travels at the same speed. This single fact forced a deep revision of how time and space behave. They could no longer be separate, absolute stages where events simply happen. Instead, they became intertwined, forming what is now called space-time, a four-dimensional fabric where time is inseparable from the three dimensions of space. In this framework, time does not flow identically for everyone. The rate at which time passes depends on motion and gravity. This is not metaphor or illusion. It is measurable, precise, and confirmed. A clock moving very fast relative to another will tick more slowly. A clock deep in a gravitational field will tick more slowly than one far away from massive objects. These effects are tiny in everyday life, but they are real and they accumulate. This immediately opens the first scientifically grounded doorway to time travel, although it is not the kind that fiction often imagines. Traveling into the future is not only possible according to physics, it is already happening. Astronauts aboard the International Space Station age slightly less than people on Earth because they are moving faster and experiencing weaker gravity. The difference is only fractions of a second, but it is exactly what Einstein's equations predict. The reason this happens is not because time itself changes its direction, but because different paths through space-time contain different amounts of time. Each object follows what physicists call a world line, a path through space-time that combines motion through space and motion through time. When that path involves high speed or strong gravity, the portion of the path that corresponds to time becomes shorter. Less time passes along it. An analogy can help here, but only briefly. Imagine two paths between the same cities, one flat and one mountainous. Both lead from the same start to the same end, but the distance traveled is not identical. In space-time, different motions create different path lengths in time, even when events begin and end together. This is not because time is being manipulated, but because time is part of the geometry being traveled through. This form of future travel has strict limits. To experience significant jumps into the future, an object would need to travel extremely close to the speed of light or remain near intense gravitational fields. Both conditions involve energies and environments far beyond current human capability. The physics allows it, but practicality quickly closes the door. Still, the key point remains. The future is accessible in principle, not by stepping outside time, but by moving through it differently. The past is a much more delicate question. Physics treats backward time travel with far greater caution, and the reasons become clear once cause and effect are examined closely. In our everyday experience, causes come before effects. This ordering feels fundamental, not because it is emotionally satisfying, but because it is deeply embedded in physical processes. Entropy increases. Systems evolve from ordered states to less ordered ones. Memory works in one direction because physical records form only when entropy rises. This one-way direction is known as the arrow of time. It does not arise from the basic laws of motion, which often work equally well forward or backward, but from statistical behavior in large systems. The universe began in an extraordinarily low entropy state, and ever since, it has been unfolding toward higher entropy. This creates a natural distinction between past and future that is not easily undone. Any attempt to travel backward in time must confront this arrow. Reversing time would mean reversing the accumulation of entropy, unbreaking eggs, unburning fuel, unmixing gases. Physics does not forbid individual microscopic processes from running backward, but it does not provide a mechanism for large-scale reversal. The universe overwhelmingly favors the forward direction because there are vastly more disordered states than ordered ones. Still, Einstein's equations of general relativity contain solutions that appear to allow paths through space-time that loop back on themselves. These paths are called closed time-like curves. In such a space-time, an object could, in theory, follow a path that returns it to its own past. This possibility emerges not from science fiction, but from the mathematics of gravity itself. One of the earliest examples was discovered by Kurt Gödel, who found that a rotating universe could allow time loops. Other solutions involve infinitely long rotating cylinders, known as Tipler cylinders, or the interiors of certain black holes. Later, physicists explored wormholes, hypothetical tunnels through space-time that could connect distant regions and possibly different times if their ends experience different gravitational or motion histories. At first glance, these solutions seem to open the door to backward time travel. But physics is not satisfied with mathematical permission alone. It demands physical plausibility. Many of these solutions require conditions that are either unphysical or unknown to exist in reality. Infinite cylinders, exotic forms of matter with negative energy density, or perfectly stable wormholes remain speculative. Even if such structures existed, deeper problems emerge. Backward time travel threatens causality, the principle that causes precede effects. Familiar paradoxes arise, not as storytelling devices, but as logical conflicts. If an event in the future can influence the past, then the chain of cause and effect can loop in ways that undermine consistency. Physics responds to this tension in several ways. One idea, proposed by Igor Novikov, is the self-consistency principle. It suggests that any event occurring on a closed time-like curve must be self-consistent. In other words, time travel to the past would be allowed only if it does not create contradictions. Events would unfold in such a way that the timeline remains internally coherent, even if it includes loops. Another approach comes from quantum mechanics. In quantum theory, outcomes are probabilistic, and systems can exist in superpositions of states. Some researchers have explored whether quantum effects could soften classical paradoxes, allowing histories to branch or interfere in ways that preserve consistency. These ideas remain active areas of research, not settled conclusions. There is also a strong argument that nature protects causality altogether. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent the formation of closed time-like curves under realistic conditions. According to this idea, quantum effects near would be time machines could become violent enough to destroy them before they form. The universe, in this view, quietly enforces its own consistency. Importantly, none of these ideas have experimental confirmation. They live at the edge of known physics, where general relativity and quantum mechanics intersect but do not yet fully agree. This boundary is not a place of fantasy, but of careful uncertainty. Physicists do not claim that time travel to the past is possible. They say only that current theories do not fully resolve the question. What remains clear is that time is not a simple river carrying everything uniformly forward. It is a dimension with structure, shaped by motion, mass, and the geometry of the universe. Time travel to the future fits comfortably within this structure, emerging naturally from relativity. Time travel to the past challenges deeper principles, pushing against causality, entropy, and consistency. As research continues, physicists refine their understanding of time not by imagining machines, but by studying black holes, gravitational waves, quantum fields, and the early universe. Each of these environments tests how time behaves under extreme conditions. So far, they reinforce a picture where time is flexible but not easily manipulated, directional but not absolute. Science does not dismiss time travel outright, nor does it embrace it casually. It treats it as a question about the nature of time itself. By asking whether time travel is possible, physics is really asking what kind of universe we inhabit, one where history is fixed, flexible, or fundamentally constrained by laws we are only beginning to understand. And so the question remains open, not as an invitation to fantasy, but as a careful exploration of the deepest structures we know. Time, as science reveals it, is more subtle than intuition suggests, more accommodating than our instincts allow, and more guarded than our stories imagine. One place where time is pushed to its limits is near a black hole, where gravity becomes so intense that space-time itself bends sharply inward. As matter approaches the event horizon, the boundary beyond which nothing can return, time for that falling matter slows dramatically when viewed from far away. Signals stretch, clocks appear to freeze, and the future of the infalling object seems to spill outward, never quite completing. This is not a trick of perception. It is a real consequence of how gravity shapes time, confirmed indirectly through observation and calculation. Inside a black hole, the behavior of time becomes even stranger, though our understanding grows uncertain. In the simplest models, time and space exchange roles. Moving forward in time becomes as unavoidable as falling inward. There is no option to stop or turn back. This extreme reshaping shows that time is not an independent stage on which gravity acts. Gravity is the curvature of space-time itself, and time is part of what curves. Because black holes represent such intense distortions, they have become natural laboratories for testing the limits of time travel ideas. Some theoretical solutions suggest that certain black holes could contain pathways that resemble tunnels through space-time. These possibilities emerge from equations, not observations, and they depend on idealized conditions that may never occur in nature. Still, they serve an important role. They reveal where known physics stretches thin, where deeper principles may intervene. Quantum mechanics adds another layer of tension. At very small scales, time behaves differently from the smooth flow described by relativity. Quantum systems evolve according to probabilities, not certainties, and time enters these equations in a more abstract way. It is a parameter that tracks change, not an object that can be bent or curved. This mismatch creates one of the central challenges in modern physics: reconciling quantum mechanics with gravity. Some researchers suspect that time, as we experience it, may not be fundamental at all. Instead, it may emerge from deeper quantum processes, much like temperature emerges from the collective motion of atoms. In this view, time travel questions become questions about emergence. Can an emergent feature be navigated independently, or is it inseparable from the underlying processes that create it? Experiments so far offer subtle clues. Quantum systems can display behavior that resembles time reversal at very small scales, where equations work equally well forward and backward. But these reversals do not accumulate into macroscopic time travel. Decoherence quickly erases them, restoring the familiar arrow of time. The boundary between quantum reversibility and classical irreversibility remains an active area of study. There are also proposals involving quantum information. Some experiments simulate closed time-like curves using entangled particles and post-selection, creating systems that behave as if information loops back on itself. These experiments do not create real time loops, but they explore how information behaves under time-like constraints. They suggest that even if time loops were possible, information might obey strict consistency rules. What becomes clear through all of this is that time travel is not a single question with a single answer. Traveling to the future fits naturally within established physics. It arises from motion and gravity, from geometry rather than machinery. Traveling to the past presses against unresolved boundaries, where equations allow possibilities that physical reality may forbid. The universe appears tolerant of time being stretched and shaped, but resistant to it being folded back on itself. This resistance may come from entropy, from quantum instability, or from principles we have not yet fully identified. Each possibility points to a universe that is flexible but not careless, permissive but not paradoxical. As scientists continue to observe gravitational waves, study the interiors of black holes through indirect signals, and probe quantum systems with increasing precision, they are not chasing time travel in the cinematic sense. They are asking how time behaves when pushed to extremes, and what those behaviors reveal about the universe as a whole. In that sense, the question of time traveling becomes a mirror. It reflects how deeply time is woven into everything else. Matter, energy, space, causality, memory, and change all depend on it. To understand whether time can be navigated is to understand whether the universe allows its own history to be rearranged, or whether history is something that, once written, becomes part of the structure itself. The quiet answer emerging so far is not dramatic, but it is profound. Time is not a simple line we move along, nor a place we step outside of. It is a dimension we inhabit, shaped by where we go and how fast we move, anchored by laws that preserve coherence even when they allow flexibility. The universe seems willing to let us glimpse our future, but it guards its past with careful consistency, holding causality together as tightly as space-time itself. When physicists talk about time travel, they often find themselves returning to a more basic question, one that quietly sits underneath all the others. Is time something that exists on its own, or is it a measure of change between physical states? This distinction matters, because if time is fundamental, it might be treated like space, something that can, in principle, be traversed in different ways. If time is instead an emergent bookkeeping tool, then traveling through it becomes a category error, like trying to step sideways through a temperature. In classical physics, time was treated as absolute. Isaac Newton imagined it as a universal clock, ticking identically everywhere, independent of what the universe was doing. This picture made time travel impossible by definition. There was only one now, shared by all things, and it advanced uniformly. Einstein dismantled this idea not by arguing against it philosophically, but by showing that it was incompatible with experiment. Once time became relative, tied to motion and gravity, it gained structure. And structure is what allows paths. Yet even in relativity, time is not a location. You cannot point to a coordinate and say, this is the past, this is the future, in the same way you point north or south. Every observer carries their own time with them. This personal time, measured by a clock following a world line, is called proper time. It is deeply local. No equation allows an object to detach from its own proper time and move freely across it. This is why all realistic discussions of time travel remain constrained. You can move through space-time in ways that change how much time you experience relative to others. You cannot step off your own timeline and choose another. Physics allows stretching, not jumping. Some of the most intriguing insights come from considering the early universe. Near the beginning of cosmic expansion, densities and temperatures were extreme. Space and time themselves were compressed into a state where classical descriptions break down. In this regime, some models suggest that time, as we understand it, may not have existed in a familiar form. Instead, change occurred without a clear temporal ordering, governed by quantum gravitational effects. This raises a subtle point. If time emerged as the universe cooled and expanded, then asking about traveling to before time existed becomes meaningless. There is no before without time. Just as there is no north of the North Pole, there may be no earlier than the earliest meaningful moment. In this sense, the universe may have a built-in temporal boundary, not enforced by walls or guards, but by the definition of time itself. Black holes echo this idea in reverse. At their centers, known as singularities in classical theory, time appears to end. Paths through space-time cannot be extended beyond certain limits. Whether singularities truly exist or are replaced by new quantum structures is still unknown, but the message is consistent. Time has edges where our current descriptions fail, and those edges are not navigable in the way space is. Another constraint comes from energy. Any mechanism that significantly distorts space-time requires enormous amounts of it. Bending time enough to create loops or shortcuts is not a small adjustment. It is an extreme act, comparable to creating or manipulating black holes. Even if exotic matter with unusual properties exists, there is no evidence that it can be controlled or stabilized at will. This practical barrier reinforces a deeper theme. Physics often allows possibilities in principle that reality never realizes in practice. The equations of fluid dynamics allow perfectly smooth flows, yet turbulence dominates most real fluids. Similarly, the equations of space-time allow exotic configurations, but the universe may strongly prefer stable, causal ones. Researchers studying quantum gravity continue to explore whether time might be discrete at the smallest scales, broken into indivisible units rather than flowing continuously. If so, time travel would face additional restrictions, much like trying to move smoothly across a staircase instead of a ramp. Early results suggest that even in such models, causality remains protected. Throughout all of this, one idea remains consistent. Physics has never observed any violation of causality. Every experiment, every observation, from particle accelerators to distant galaxies, respects the ordering of cause and effect. This does not prove that backward time travel is impossible, but it places a heavy burden on any theory that allows it. The scientific attitude toward time travel is therefore neither dismissive nor permissive. It is cautious, grounded, and precise. Physicists follow where equations lead, but they test those paths against reality, against stability, against consistency. When conflicts arise, they look for deeper principles, not loopholes. What science says about time traveling is not delivered as a verdict, but as a landscape. Some directions are open and gently sloped. Others rise steeply and vanish into fog. The future lies along paths that are difficult but clearly defined. The past lies behind barriers that may be mathematical artifacts, or may reflect something fundamental about how the universe preserves coherence. Time, it seems, is not a road we walk along freely. It is a structure we are embedded within, shaped by motion, gravity, and the large-scale history of the cosmos. We move forward through it not by choice, but by participation, carried by processes that link memory, causality, and change into a single, consistent flow. And within that flow, physics continues to listen carefully, asking not how to escape time, but how time itself comes to be the way it is. Another way physicists approach time travel is by asking how tightly time is linked to information. Every physical process leaves traces. Particles scatter, atoms vibrate, radiation carries imprints of what occurred. This accumulation of records is not incidental. It is central to why the past feels fixed. Once information has spread into many degrees of freedom, retrieving and reversing it becomes effectively impossible. Time's direction is reinforced not by law alone, but by the dispersal of information into the environment. This perspective reframes the problem. Traveling to the past would not only require bending space-time, it would require gathering and reorganizing information that has already diffused throughout the universe. The challenge is not just mechanical, but informational. Physics offers no mechanism for collecting every photon, every thermal fluctuation, every microscopic trace and restoring them to a prior arrangement. The past is not hidden behind a door. It is dissolved into the present. Quantum theory sharpens this idea. In quantum mechanics, information is conserved, but it is also easily entangled. Once systems interact, their states become linked in ways that cannot be undone locally. Entanglement spreads rapidly, tying the fate of small systems to vast environments. This creates a one-way cascade. Even though the underlying equations allow reversibility, the practical loss of control makes reversal inaccessible. Some researchers have explored whether quantum correlations could permit limited forms of retrocausality, where future measurements influence past states in subtle ways. These effects do not allow messages to be sent backward in time. They do not permit changes to recorded history. Instead, they reveal that at the quantum level, temporal order can be less rigid than everyday experience suggests, while still preserving overall consistency. This distinction matters. Physics is comfortable with counterintuitive behavior as long as it does not allow contradictions. The universe tolerates strangeness. It does not tolerate inconsistency. Every serious proposal involving time must satisfy this requirement, or it is set aside. Even space-time itself appears to enforce this discipline. When theorists attempt to construct time-looping geometries, quantum fields within those geometries often become unstable. Energy densities grow without bound. Fluctuations amplify instead of settling. These reactions look less like invitations and more like warnings, as though space-time resists being folded in ways that undermine cause and effect. In this sense, time travel becomes a diagnostic tool. By probing its limits, physicists learn what the universe values: stability, coherence, predictability. These are not philosophical preferences, but physical ones, emerging from equations that describe how reality behaves when pushed. What remains striking is how little of this relies on speculation about machines or technology. The conversation stays grounded in clocks, particles, gravity, and information. Time travel is not treated as an engineering challenge awaiting clever design. It is treated as a question about the architecture of reality itself. And that architecture, as far as current science can tell, allows time to stretch and compress, to pass at different rates, to intertwine with space in elegant ways. It allows observers to age differently, futures to be reached by taking unusual paths. But it draws a quiet boundary around the past, not as a prohibition announced loudly, but as a condition woven into entropy, information, and geometry. So, when science speaks about time traveling, it does so carefully. It says yes to the future under precise circumstances. It remains undecided about the past, while steadily uncovering reasons why returning may be incompatible with how the universe maintains order. The question stays alive, not because answers are imminent, but because exploring it continues to reveal what time truly is and what it refuses to be. Another quiet constraint appears when physicists examine how time is actually measured. Time in science is not an abstract river. It is defined operationally by physical processes that repeat in regular ways. Atomic clocks count the oscillations of electrons in cesium atoms. Astronomical time once came from the rotation of Earth. In every case, time is inseparable from change. Without change, there is no clock, and without clocks, time has no physical meaning. This matters because time travel would require more than motion through coordinates. It would require physical processes to unfold in an order that contradicts how those processes generate time in the first place. A clock carried backward would still tick forward according to its own internal dynamics. No known mechanism allows a physical system to evolve in reverse while remaining stable and intact. Relativity reinforces this point. Each object carries its own proper time, determined by its motion and gravitational environment. Proper time always increases along a physical path. This is not a preference. It is built into the geometry of space-time. Even in spacetimes that allow loops mathematically, the local experience of time along any path remains forward-moving. The loop exists globally, not locally, and that distinction proves crucial. To create a genuine return to the past, an object would need to follow a path that reconnects with an earlier space-time event while maintaining physical continuity. Most proposed solutions either require infinite structures, perfect symmetries, or conditions that destabilize under the slightest disturbance. The moment realistic physics is added, these paths tend to collapse. This fragility suggests that time travel, if it exists at all, would be extraordinarily sensitive. Any interaction, any stray particle, any quantum fluctuation could disrupt it. Nature seems comfortable with time dilation, where differences accumulate smoothly. It appears hostile to time reversal, where precision would need to be absolute. The universe's expansion adds another layer. Space itself is stretching, carrying galaxies apart. This expansion defines a cosmic time, measured by observers moving with the overall flow of matter. On large scales, this time provides a shared ordering of events. It is not absolute in the Newtonian sense, but it is remarkably consistent across the observable universe. Traveling far into the past would mean moving against this expansion, not just locally, but cosmically. It would require undoing the large-scale evolution of space-time itself. The energy required to reverse even a small region would dwarf anything accessible to known physics. The past is not merely behind us. It is embedded in the universe's growth. There is also the question of identity. Physics tracks objects through time by conserving quantities like energy, momentum, and charge. These quantities allow systems to be recognized as the same system at different moments. If time travel to the past were possible, these conservation laws would face new challenges. An object appearing twice at the same time would double its conserved quantities unless compensated in some unknown way. Attempts to resolve this often lead back to self-consistency conditions, where events are constrained to avoid contradiction. But such constraints begin to look less like freedom and more like predetermination. The past could not be changed, only fulfilled. Time travel would lose the very flexibility that makes it appealing in imagination. Quantum field theory deepens the difficulty. Fields fill all of space-time. Particles are excitations of these fields, not isolated beads moving through emptiness. Rewinding a particle would require rewinding the state of the field everywhere it has interacted. That influence propagates outward at the speed of light, entangling the particle's history with the rest of the universe. This is why many physicists suspect that time travel to the past is not forbidden by a single rule, but by the combined weight of many. Geometry resists it. Entropy undermines it. Information dispersal locks it. Conservation laws strain under it. Each obstacle alone might be negotiable. Together, they form a structure that quietly holds. Still, the future remains open. Relativity treats the future as something that can be reached at different rates. This does not violate causality, because causes still precede effects along every world line. The order of events remains intact even when clocks disagree. The universe permits diversity of experience without contradiction. This difference between future and past travel is not symmetrical. The laws of physics may look symmetric in equations, but their solutions are not equally realized. Initial conditions matter. The low entropy beginning of the universe set a direction that has never been reversed on large scales. Some scientists have asked whether advanced civilizations could exploit extreme environments to achieve dramatic time dilation. Skimming the edge of a rotating black hole, for example, could allow years to pass elsewhere while days pass locally. This is still future travel, not reversal, but it highlights how far physics allows time to be stretched without breaking. These scenarios are not fantasies. They are calculations. But they remain far beyond practical reach, and they come with immense risks. The closer one approaches such extremes, the less forgiving the environment becomes. Tidal forces, radiation, and instability rise sharply. Nature does not offer shortcuts without cost. Through all of this, time emerges not as a resource to be spent or saved, but as a relationship between processes. It links change to change, event to event. When science speaks about time travel, it is really speaking about how flexible those relationships can be without collapsing into contradiction. The quiet answer that physics offers so far is subtle. Time is malleable in rate, but rigid in order. It can be experienced differently, but it resists being rearranged. The universe allows us to arrive late to the future, but it does not invite us to revisit what has already unfolded. This does not close the question. It sharpens it. By understanding why time travel is difficult, science reveals what time is made of. Geometry, entropy, information, and causality are not separate ingredients. They are aspects of a single structure that gives time its character. And within that structure, inquiry continues. Not in search of a machine, but in search of coherence. Each experiment, each observation, each refinement of theory brings a time into clearer focus, not as a path to escape, but as a dimension to understand, patiently, honestly, and with care. What makes time travel feel tempting is not speed or technology, but the intuition that time might be another direction hidden from us. Space offers choices. You can move left or right, forward or back. Standing still feels optional. Time does not grant that freedom. Every physical system advances along it, and nothing observed has ever paused or reversed its own progression. That asymmetry is the seed of the question. If space can be navigated, why not time? To approach that, physics first strips away human intuition and looks at how motion is actually described. In relativity, objects do not move through space alone. They move through space-time. Even when you are standing still relative to your surroundings, you are moving through time at the maximum possible rate. Motion through space reduces motion through time, not because time slows arbitrarily, but because space-time has a fixed structure. There is only so much motion to distribute. Seen this way, time travel to the future becomes less mysterious. Increase motion through space, and less motion remains for time. That trade-off is built into the geometry of reality. High-speed flight, intense gravity, or both can shift how much time accumulates along a path. Nothing about this requires speculation. It has been measured with airplanes, satellites, and atomic clocks. The universe confirms it quietly and consistently. Backward motion is different. There is no known trade-off that converts spatial motion into negative time. Space-time geometry allows slowing but not reversal along any physical path. Proper time always increases. This is not an added rule. It is a consequence of how distances are defined in space-time itself. Trying to reverse time would mean following a path with negative length in time, something that does not correspond to any known physical process. Black holes push these ideas to extremes. Near them, time dilation becomes severe. Faraway observers see in-falling matter slow almost to a halt. Yet for the falling object itself, nothing special happens at the horizon. Its clock continues forward, steadily, irreversibly. Even here, where space-time is violently curved, local time refuses to turn around. Inside such regions, theory becomes uncertain, but one pattern holds. Every physically allowed trajectory carries a time forward along it. The past is not reachable by retracing steps. Paths do not intersect earlier versions of themselves in any controlled, stable way. Mathematical curiosities may suggest otherwise, but physical consistency pulls back. Entropy strengthens this picture. Every macroscopic process leaves behind disorder. Heat spreads, information disperses, correlations weaken. This is not a psychological arrow, it is statistical inevitability. Reversing time would require reversing entropy, not locally, but across every interaction involved. Physics does not prohibit this in principle for tiny systems, but it offers no method for achieving it in large ones. Even imagining such control exposes deeper issues. A traveler returning to an earlier time would carry memories, structure, and information that did not previously exist. That information would need an origin consistent with conservation laws. Nothing in known physics provides a way to insert information into the past without accounting for its source. Quantum mechanics adds subtlety without granting freedom. At microscopic scales, processes can be time-symmetric. Equations do not prefer a direction. But the moment systems interact with environments, that symmetry dissolves. Entanglement spreads. Correlations leak outward, and reversibility vanishes in practice. The arrow of time reasserts itself not by decree, but by loss of control. Some laboratory experiments mimic time reversal by carefully manipulating quantum states. These demonstrations are impressive, but they are not time travel. They work only because the system is isolated, engineered, and fragile. Scaling such behavior to complex objects would require control beyond any realistic possibility. The universe does not naturally maintain such delicacy. Speculation often turns to wormholes as potential bridges between times. In theory, if one mouth of a wormhole experienced extreme time dilation relative to the other, their clocks could desynchronize. Passing through might then resemble travel into the past. This idea emerges from valid equations, but it depends on exotic matter that has never been observed and may not exist in stable form. Even granting such matter, wormholes appear violently unstable. Quantum fluctuations would likely collapse them instantly. Attempts to stabilize them introduce runaway energies that destroy the configuration. Again, equations open a door that physics itself seems eager to close. Causality remains the organizing principle behind these closures. Causes precede effects in every verified observation. When proposed mechanisms threaten this ordering, they encounter resistance from multiple directions at once. No single law forbids backward time travel. Instead, a network of constraints converges, each reinforcing the others. Information theory frames this convergence clearly. Once information has been copied into many degrees of freedom, reversing it requires gathering and coordinating those degrees perfectly. The universe does not keep spare copies neatly arranged. Information spreads, decoheres, thermalizes. The past becomes encoded everywhere, which is another way of saying it becomes inaccessible. Cosmology reinforces this on the largest scales. The universe has been expanding from a hot, dense beginning. This expansion defines a global sense of earlier and later. Galaxies separate, radiation cools, structures form. Reversing time would require reversing this entire history, not just a local region. There's no indication that space-time permits such selective undoing. The beginning of the universe itself sharpens the point. Near the Big Bang, familiar time loses meaning. Some models describe a phase where time, as a parameter, ceases to exist. If time emerged, then travel before its emergence is undefined. Physics does not merely lack a mechanism, it lacks a reference. Similarly, certain models suggest that deep inside black holes, time may terminate. Not reverse, not loop, but end. These edges hint that time is not infinite in all directions. It has boundaries defined by physical conditions, not by choice. What remains is a universe that treats time asymmetrically by construction. Forward evolution builds complexity. Backward evolution demands impossible precision. This imbalance is not an accident. It is a consequence of how physical laws, initial conditions, and statistics interact. Future-directed time travel fits into this framework cleanly. It respects causality. It preserves information flow. It aligns with entropy. It emerges naturally from motion and gravity. The universe allows it without strain, even if achieving it dramatically is impractical. Past directed time travel conflicts with each of these pillars. It demands geometry that destabilizes, entropy that reverses, information that recollects, and causality that loops. No experiment hints that such coordination is possible. Science, therefore, speaks about time travel with careful clarity. It does not dismiss curiosity. It channels it. By asking what would be required, physics reveals what time actually is. Not a corridor to Rome, but a dimension that orders change, locks in history, and allows variety without contradiction. Seen from this angle, time travel is not a failure of imagination. It is a probe. Pushing against its limits shows where the structure of reality becomes firm. The universe bends willingly in some ways, and resists firmly in others. Time stretches. Time slows. Time diverges between observers. These are not metaphors. They are measurements. But time does not rearrange itself freely. It does not grant access to what has already unfolded. That may be the most scientific answer available. Not a prohibition etched into law, but a pattern observed across scales. Wherever physics has been tested, time behaves as a one-way ordering of events, flexible in pace, fixed in direction. And within that ordering, inquiry continues. Each attempt to understand time travel sharpens understanding of space-time, entropy, information, and causality. The question remains valuable not because it promises escape, but because it reveals how deeply time is woven into everything that exists. What becomes especially revealing is how time behaves when physics tries to describe the universe as a whole rather than isolated systems. When cosmologists model the universe, they do not begin with clocks or calendars. They begin with symmetries, energy distributions, and equations that describe how space-time evolves. Time, in this context, is not assumed. It emerges as a parameter that orders change as the universe expands. Early in the universe's history, conditions were so extreme that familiar distinctions blur. Temperatures were immense, densities enormous, and quantum effects dominated everything. In this regime, many physicists suspect that time as we experience it did not yet exist in a meaningful way. Equations describing quantum gravity often do not contain time explicitly. Instead, they describe relationships between states. Change occurs, but without a preferred temporal ordering. This idea reshapes the time travel question at its root. If time emerged from a deeper, timeless description, then traveling through time may be like trying to navigate a wave by stepping outside the ocean. The wave exists only because of the medium beneath it. Remove the medium and the concept dissolves. Julian Barber, among others, has argued that time may be an illusion arising from change itself. In this view, the universe is a collection of possible configurations, and what we call time is simply the ordering of these configurations according to how well they record one another. Memory creates direction. Records create sequence. Without records, there is no past to return to. Even if one does not adopt this interpretation fully, it highlights a key constraint. The past is not just earlier moments. It is earlier configurations that are encoded into the present. Fossils, photons, memories, cosmic background radiation all carry information forward. This forward carrying is irreversible in practice. The past persists only as imprint, not as location. Attempts to formalize time travel mathematically often encounter this informational wall. Closed time-like curves appear to permit return, but they do not restore erased information. Instead, they force consistency. Whatever happens must already be woven into the structure of events. Free alteration disappears. From this perspective, backward time travel would not resemble revisiting a moment and choosing differently. It would resemble discovering that the moment was always shaped by the visit. The freedom imagined evaporates under physical scrutiny. Quantum gravity research continues to explore whether space-time itself is granular, composed of discrete elements rather than a smooth continuum. Loop quantum gravity, causal set theory, and related approaches suggest that spacetime may be built from fundamental units linked by causal relations. In these models, causality is not imposed afterward. It is the skeleton from which spacetime grows. If causality is fundamental, then time travel to the past would require violating the very links that define spacetime's structure. That is not merely difficult, it is contradictory. The structure would unravel. Even string theory, which allows for extra dimensions and exotic geometries, maintains causal consistency at observable scales. While the mathematics becomes elaborate, the physical predictions preserve ordered cause and effect. Time remains directional where it matters. What is striking is that these conclusions arise independently across approaches. Different theories, different languages, same pattern. Time bends. Time stretches. Time differs between observers. But time does not loosen its grip on order. When physicists examine experimental evidence, the pattern sharpens further. Particle accelerators probe energies unimaginable a century ago. Precision clocks detect minuscule relativistic effects. Astronomical observations trace light that has traveled billions of years. None show violations of causality. None hint at signals arriving before they were sent. This absence is not trivial. If backward time travel were easy or common, even at microscopic scales, traces would appear. Nature leaves footprints everywhere. The silence is meaningful. That silence does not imply stagnation. Instead, it points toward a universe that is dynamic yet disciplined. Time is flexible enough to allow relativity, but firm enough to protect coherence. This balance is delicate, and it appears intentional in the mathematical sense. Alter one aspect too much, and the structure collapses. Consider again future-directed time travel. It aligns naturally with everything else. Entropy increases. Information spreads. Causality holds. Motion and gravity redistribute time without contradiction. This harmony suggests that future travel is not an exception, it is a feature. Backward travel stands apart because it demands simultaneous violation of multiple principles. Each principle is supported independently. Together, they form a barrier that is not absolute in equation, but overwhelming in practice. This does not make the question trivial. On the contrary, it makes it powerful. By asking about time travel, physics uncovers why time has the properties it does. Direction, irreversibility, locality, and memory are not separate mysteries. They are facets of one structure. As understanding deepens, the focus shifts. Less attention is paid to traveling through time, and more to understanding how time emerges, how it interacts with quantum information, how it behaves near singularities, and how it shaped the early universe. These investigations do not promise dramatic journeys. They promise clarity. Clarity reveals a universe that is not hostile to curiosity, but precise in its allowances. It permits exploration within boundaries that preserve coherence. Time is one of those boundaries, not as a wall, but as a framework. Within that framework, change unfolds. Stars ignite and fade. Galaxies collide. Consciousness arises briefly and reflects. All of it occurs within time, not as an external parameter, but as an intrinsic ordering of events. Science, at its most careful, does not romanticize this. It observes it. The picture that emerges is neither bleak nor fantastical. It is quietly astonishing. A universe where time is real, malleable, directional, and deeply woven into everything that happens. The question of time travel remains valuable, not because it promises escape, but because it sharpens understanding. Each constraint teaches something. Each impossibility reveals structure. And so the exploration continues, not toward machines or portals, but toward deeper descriptions of reality. Time, as science describes it, is not something to conquer. It is something to understand, patiently, rigorously, and with growing appreciation for how much order it quietly maintains. Another layer becomes visible when time is examined not as a backdrop for events, but as something inseparable from measurement itself. In physics, nothing is measured without interaction. A clock works only because it changes state in a regular way, and because that change can be compared to something else. Time, in practice, is always relational. One process is timed against another. This relational nature quietly restricts what time travel could mean. Imagine attempting to move backward in time without altering anything else. The very act of observation would already break the condition. To register arrival, a measurement must occur. That measurement creates a record. Records only form in one temporal direction because they require irreversible physical change. The moment something is observed, entropy increases. This means that arriving in the past without disturbing it is not merely difficult. It contradicts how measurement works at a fundamental level. Even more revealing is how relativity handles simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another who is moving differently. There is no universal present moment shared by the entire universe. Instead, each observer carries their own slicing of space-time into past, present, and future. This relativity of simultaneity dissolves the idea of a single objective past that everyone could return to. If no universal present exists, then the past itself is not a single global place. It is a collection of observer-dependent descriptions. Traveling to the past would require choosing which observer's past is meant, which space-time slicing is privileged. Physics offers no such privilege. All inertial frames are equally valid. The equations refuse to elevate one timeline above the others. This alone undermines many intuitive pictures of time travel. Stories often imagine a fixed historical landscape waiting to be revisited. Relativity replaces that landscape with a web of intersecting world lines, each with its own notion of earlier and later. There is no master timeline to step into. Gravitational fields complicate this further. Near massive objects, time passes at different rates. Two observers at different heights in a gravitational field will disagree about how much time has elapsed between the same pair of events. This is not subjective. It is measurable and real. The past, therefore, is not uniformly layered beneath the present. It is warped, uneven, and observer-dependent. Because of this, traveling to a specific moment would require specifying a precise space-time event, not a date or era. That event is defined by coordinates that depend on the entire gravitational and kinematic context of the universe. Any slight change alters the coordinate system itself. Precision becomes unattainable. Attention then turns to causality again, not as an abstract principle, but as a practical organizing rule. Causality ensures that signals propagate within light cones, regions of space-time that define what can influence what. These cones structure reality. They prevent distant events from interacting arbitrarily. Time travel to the past would require crossing light cones in forbidden ways. In theoretical models that permit such crossings, new problems arise immediately. Quantum fields respond violently. Energy densities grow. Vacuum fluctuations amplify. The closer one approaches a causality violation, the more unstable the environment becomes. These reactions appear consistently across different calculations, suggesting a built-in resistance rather than an accidental flaw. Stephen Hawking's chronology protection idea captures this intuition without relying on a single mechanism. It proposes that the laws of physics act collectively to prevent macroscopic violations of causality, not by decree, but by instability. Attempts to form time loops trigger processes that destroy the conditions needed to sustain them. This kind of protection is subtle. It does not forbid strange geometries outright. It allows equations to explore them. But it ensures that physical reality does not settle into those configurations. The universe, in this view, tolerates imagination while enforcing coherence. Thermodynamics adds weight to this enforcement. The second law does not merely describe heat flow. It governs the likelihood of processes. While microscopic reversals are possible, macroscopic reversals are overwhelmingly unlikely. Time travel to the past would require an astronomical coincidence of reversals occurring in perfect coordination. Physics does not ban coincidence. It renders it vanishingly improbable. Probability, in this sense, becomes a practical law. The universe does not need to forbid impossible events if it can suppress them so completely that they never occur. Time travel to the past may belong to this category, allowed on paper, absent in reality. Even discussions of advanced civilizations encounter this barrier. Speculation sometimes imagines technology so powerful that it could manipulate space-time freely. Yet greater power does not grant exemption from fundamental constraints. More energy amplifies gravitational effects, but it also amplifies instability. Approaching the limits of space-time curvature invites collapse, not control. Rotating black holes illustrate this tension. Their extreme structure allows regions where space-time is dragged around rapidly. Some theoretical paths near these objects resemble time loops, but these regions are also filled with intense radiation and instability. Surviving them long enough to exploit any exotic behavior appears implausible. Wormholes face similar issues. Keeping them open requires negative energy densities. Quantum field theory allows small amounts of negative energy in fleeting configurations, but scaling this up leads to violations of known energy conditions. Attempts to stabilize wormholes trigger runaway effects that close them or destroy surrounding space-time. Each proposal encounters resistance from a different direction, yet the outcome converges. Backward time travel remains mathematically intriguing and physically elusive. What stands out is how consistently time travel questions illuminate the nature of time itself. Time is not just another coordinate. It is the parameter that orders change, anchors causality, and ties physical processes together. Altering it threatens the relationships that make physics predictive. This predictability is not optional. Without it, science collapses. Experiments rely on repeatability. Theories rely on consistency. Time travel that disrupts causality would erode both. The absence of such disruptions is not merely comforting. It is necessary for knowledge to exist at all. Quantum interpretations sometimes raise questions about branching timelines or many worlds. In these frameworks, all possible outcomes occur, but they do so in separate, non-interacting branches. Importantly, these interpretations do not permit travel between branches. They preserve local causality within each branch. The past of any given branch remains fixed. Such ideas are often misunderstood as enabling time travel. They do not. They simply reframe probability. The structure of time within each history remains intact. Closer examination reveals a consistent theme. Whenever physics allows flexibility, it also installs safeguards. Relativity allows time dilation, but preserves local order. Quantum mechanics allows superposition, but enforces consistency through measurement. Thermodynamics allows fluctuations, but suppresses large-scale reversals. Time travel to the future aligns with these safeguards. Time travel to the past collides with them. This asymmetry is not imposed externally. It arises naturally from the interplay of laws and initial conditions. The low entropy beginning of the universe established a direction. Everything since has unfolded along it. Memory itself depends on this direction. Brains store information by increasing entropy. Recalling the past does not retrieve it. It reconstructs it using present records. There is no cognitive mechanism for accessing an earlier state directly. Conscious experience mirrors physical law. That mirroring is not coincidence. Minds evolved within time. They reflect its structure. The impossibility of remembering the future is not just psychological, it is physical. The future has not yet left records. In this sense, time travel stories resonate because they push against deep constraints that shape existence. They explore what it would mean to violate the ordering that underlies memory, identity, and causation. Science responds not with dismissal, but with explanation. Explanation reveals a universe that is generous in complexity, but strict in consistency. Time can slow, stretch, diverge between observers, and intertwine with space. It cannot be rearranged without unraveling the very fabric that allows events to make sense. What science says about time traveling, then, is embedded in everything it says about time itself. Time is not a place to visit. It is a structure that connects moments into histories. Those histories are not interchangeable. They are constrained by laws that operate everywhere they have been tested. Understanding this does not diminish wonder, it redirects it. The true strangeness is not that time travel may be impossible, but that time is flexible at all, that clocks can disagree, that gravity can slow aging, that motion reshapes duration. These features are real, measured, and quietly astonishing. They reveal a universe where time is dynamic, not absolute, but also not arbitrary. A universe that permits variation without chaos. Within that universe, the question of time travel remains a lens. Through it, physics examines its own foundations, tests its limits, and clarifies what must remain fixed for anything to happen at all. Modern experiments give this abstract discussion a firm footing. Precision timing has reached a level where differences in time are no longer philosophical curiosities, but engineering concerns. Satellites orbiting Earth must constantly correct their clocks because motion and gravity alter the passage of time measurably. Without these corrections, navigation systems would drift by kilometers each day. Time dilation is not a speculative effect. It is a daily operational fact. Such experiments reinforce an important boundary. Every confirmed manipulation of time involves changing its rate, not its direction. Clocks disagree, but none run backward. The equations allow slowing, stretching, offsetting. They never produce reversal in any physically realized system. This distinction persists no matter how refined the measurements become. Observations of distant astrophysical phenomena extend this picture across billions of years. Light arriving from faraway galaxies carries timestamps encoded in atomic transitions and spectral lines. Those timestamps align with models of cosmic expansion and gravitational influence. Time behaves consistently across immense distances and durations. No observation hints at messages arriving before their sources emit them. Gravitational waves provide another test. These ripples in space-time propagate at the speed of light, carrying information about cataclysmic events such as black hole mergers. Detectors observe them arriving in precise temporal order, matching predictions of general relativity. The waves do not anticipate their sources. Cause and effect remain aligned even under extreme space-time distortion. Laboratory tests push closer to the quantum domain. Experiments with ultra-cold atoms and superconducting circuits probe how time emerges in quantum systems. Researchers observe how coherence decays, how entanglement spreads, how reversibility fades as systems grow more complex. Small systems can be nudged into brief reversals under careful control. Larger ones cannot. Complexity locks time's direction in place. The same pattern appears in studies of chaos. Chaotic systems are highly sensitive to initial conditions. Even tiny uncertainties grow rapidly. Reversing such systems would require specifying their initial state with impossible precision. Time's arrow is reinforced by instability. The more complex a system becomes, the more strongly it resists reversal. Complexity is not incidental. The universe builds it relentlessly. Stars form heavy elements. Chemistry assembles molecules. Biology constructs self-replicating structures. Each step increases the number of interacting components and the spread of information. The forward march of time is accompanied by a forward march of complexity, and the two become inseparable. This relationship between time and complexity sheds light on identity. Objects persist through time because their internal processes maintain coherence. A living organism remains the same organism because its structure is continuously repaired and regulated. Reversing time would not merely move the organism backward. It would require reversing every repair, every interaction, every exchange with the environment. Identity, then, is time-bound. It depends on forward continuity. Time travel narratives often imagine preserving identity while relocating in time. Physics offers no mechanism for this preservation under reversal. The very processes that sustain identity operate in one temporal direction. Attention sometimes turns to closed universes or cyclic cosmologies as possible loopholes. If the universe repeats itself, could time loop naturally? Modern cosmology finds little support for exact cycles. Even models that allow contraction and rebirth predict changes between cycles. Entropy accumulates. Conditions differ. Repetition is imperfect. The arrow persists. Other proposals suggest that time might be symmetric overall, with a mirror universe evolving backward from the Big Bang. These ideas remain speculative and do not permit travel between directions. Each universe would experience its own forward time. Symmetry would exist globally, not locally. Locality remains crucial. Physics operates through local interactions. Forces propagate through space at finite speeds. This locality ensures that influences spread gradually, respecting light cones. Time travel to the past would violate locality by allowing distant events to affect earlier ones without intermediate propagation. No verified theory permits such behavior. Efforts to quantize gravity aim to unify these insights. Whether space-time emerges from entanglement, from discrete causal sets, or from vibrating strings, causality appears central. Time ordering is built into the foundations. It is not added later. Attempts to remove or invert it destabilize the structure. This foundational role of causality reframes the original question. Asking whether time travel is possible becomes equivalent to asking whether the universe can remain intelligible while allowing it. Every known path toward backward time travel erodes intelligibility. Predictions fail. Conservation laws strain. Information accounting breaks down. The resistance encountered is not arbitrary. It reflects the conditions required for physical law itself. Laws describe regularities across time. If time were freely rearrangeable, regularity would dissolve. Science would lose its footing. The fact that science works is indirect evidence that time is constrained. Conscious experience aligns with this constraint. Awareness unfolds sequentially. Perception integrates information over time. Memory accumulates. Anticipation projects forward. There is no experiential access to future memories or past sensations except through records. Mind mirrors matter not by coincidence, but because both obey the same temporal structure. This does not mean that time is subjective. It means that subjectivity is time-bound. The arrow of experience follows the arrow of physics. Both arise from the same asymmetry in how information is processed and stored. Speculation remains alive at the frontier. Researchers explore whether exotic quantum states could create limited causal loops at microscopic scales. Others investigate whether space-time foam might allow fleeting violations. These ideas are pursued cautiously, with full awareness of the constraints they face. None currently offer a path to macroscopic time travel. What emerges instead is a richer understanding of time's texture. Time is elastic but directional, local but interconnected, measurable but relational. It is neither an illusion nor a simple backdrop. It is an active participant in physical processes. Understanding this texture clarifies why time travel captivates imagination. It represents a desire to step outside constraints that shape existence. Physics responds by revealing that those constraints are not arbitrary restrictions. They are the framework that allows structure, memory, and meaning to arise. The universe does not appear designed to accommodate revision. It appears designed to accommodate evolution. States lead to other states. Causes generate effects. Records accumulate. This chain creates history, not as a story that can be edited, but as a structure that supports everything else. Within this structure, future-directed time travel remains an extension of ordinary motion. Extreme motion and gravity exaggerate familiar effects. They do not overturn order. The future becomes reachable by unusual routes, but it remains the future relative to every traveler. Backward travel, by contrast, would require rewriting the structure itself. Every attempt to describe it reveals the depth of the structure's interdependence. Geometry, entropy, information, locality, identity, and law are intertwined. Pulling on one thread unravels the rest. Science does not close the question with certainty. It narrows it. It replaces fantasy with constraint, and constraint with insight. Each barrier teaches something about what time is and why it behaves as it does. That teaching continues through observation and theory, not through speculation alone. New instruments probe deeper. New models test assumptions. Time remains central, not as a destination, but as the medium in which understanding unfolds. Another perspective sharpens when black holes are considered not as exotic objects, but as accounting systems for information. Over the past several decades, physicists have realized that black holes obey laws strikingly similar to thermodynamics. They have temperature, entropy, and limits on how much information they can contain. This realization transformed black holes from curiosities into testing grounds for the deepest ideas about time. Entropy is the key. A black hole's entropy is proportional not to its volume, but to the area of its event horizon. This suggests that information about everything that falls in is stored, in some form, on a two-dimensional surface. This insight led to the holographic principle, the idea that the physics inside a region of space can be fully described by information on its boundary. Time plays a subtle role here. When something falls toward a black hole, outside observers never see it cross the horizon. Its process is slow, its signals redshift, its information appears to smear across the surface. From the outside, the infalling object becomes frozen into the black hole's present. From the inside, however, time continues forward until extreme conditions are reached. This dual description is not a contradiction. It is a reflection of how time depends on the observer's position in space-time. Yet both descriptions preserve causality. No signal emerges from inside the horizon. No information escapes faster than light. The past outside the black hole remains intact. The black hole information paradox arose when Stephen Hawking showed that black holes emit radiation. Over immense timescales, they can evaporate. If they disappear completely, what happens to the information they contained? If information is destroyed, then the future would fail to encode the past fully. Time's ordering would break. Decades of work have converged on a remarkable conclusion. Information is not destroyed. It is preserved, scrambled, and released in subtle correlations within the radiation. This resolution preserves unitarity, a core principle of quantum mechanics. Time evolution remains consistent and reversible at the deepest level, even when appearances suggest otherwise. What matters for time travel is the implication. Even in the most extreme environments known, where space-time curvature becomes enormous, physics fights to preserve information and causal order. The universe tolerates immense distortion, but it does not tolerate erasure of history. The holographic principle strengthens this intuition. If information about a region is encoded on its boundary, then the past of that region is never lost. It is distributed, not erased. Traveling back would require decoding and reconstructing this distributed record in a way that violates locality and causality. No known mechanism allows this. Quantum entanglement adds another layer. Entangled systems share correlations that persist across distance, but these correlations cannot transmit usable information faster than light or backward in time. Entanglement respects causal order, even while defying classical intuition. It bends expectations without breaking consistency. Some modern theories go further, proposing that space-time itself emerges from patterns of entanglement. In these views, geometry arises because quantum systems are correlated in specific ways. Time, then, is not fundamental. It is a bookkeeping parameter describing how entanglement patterns change. If space-time emerges from entanglement, then altering time would require altering the underlying entanglement structure. That structure is vast, distributed across countless degrees of freedom. Rearranging it to produce a controlled return to the past would require coordination beyond anything physics allows. Notice how the question has shifted. Time travel is no longer about motion or machines. It becomes a question about whether the universe permits its informational foundation to be rearranged arbitrarily. Every indication suggests it does not. Even hypothetical scenarios involving advanced intelligence face this barrier. Intelligence can optimize processes, predict outcomes, and exploit available structures. It cannot override foundational constraints without collapsing the system it operates within. A universe that allowed free manipulation of time would undermine the reliability of physical law itself. Reliability is not a philosophical preference. It is a requirement for stability. Stars burn predictably. Atoms bond consistently. Forces act locally. These regularities depend on time ordering. Remove that ordering, and the processes that sustain structure fail. Consider again how physics treats symmetry. Many fundamental equations are symmetric under time reversal. Yet the universe is not symmetric in its solutions. This gap between law and outcome is bridged by initial conditions. A low entropy beginning selects a direction. That selection echoes everywhere. From that echo arises memory, evolution, complexity, and meaning. Time travel to the past would disrupt that echo. It would insert new information into earlier conditions, altering the cascade that produced everything that followed. Physics resists this not by decree, but by making it dynamically unstable. Dynamic instability appears again and again. Whenever models allow backward influence, small fluctuations grow uncontrollably. Energy diverges. Predictions fail. These are signs that the configuration cannot exist as a stable state of the universe. Future-directed time manipulation shows the opposite behavior. Slow time and systems remain stable. Speed them up relative to others, and equations hold. Stability persists because causal order is preserved locally. The contrast is striking. One direction integrates smoothly with everything else physics describes. The other collides with nearly every pillar at once. Seen from this angle, science does not merely say that time travel to the past is unlikely. It suggests that time's direction is part of the universe's error correction. It prevents contradictions from amplifying. It ensures that small uncertainties do not destroy large-scale order. This idea aligns with modern views of information theory. Systems that preserve information flow in one direction can correct errors, store records, and remain coherent. Systems that allow unrestricted feedback from future to past become unstable. Feedback loops explode. Time's arrow may therefore function as a stabilizing feature, not an arbitrary rule, but a necessity for complex systems to exist at all. The fascination with time travel persists because it highlights this feature by contrast. Imagining its violation makes the structure it protects visible. By pushing against the idea, science reveals what would break, and in doing so, clarifies what must remain intact. Every serious analysis converges on this realization. Time is not merely something that happens to the universe. It is part of what keeps the universe intelligible. Physics continues to refine this understanding through experiments that test ever finer temporal effects. Through observations that trace history deeper into cosmic pasts, and through theories that attempt to unify gravity and quantum mechanics without sacrificing causality. None of these efforts aim to build a path into yesterday. They aim to understand why yesterday is inaccessible in the first place. And in that understanding, the question of time traveling transforms. It stops being about movement across dates and becomes a question about the nature of reality. What kind of universe allows histories to be rewritten? What kind of universe enforces order? All evidence so far points toward the latter. A universe flexible enough to surprise, strict enough to remain coherent. Time in that universe is not an obstacle. It is a framework. It shapes what can happen without dictating every outcome. It allows difference without contradiction. That balance is subtle. It is also fragile. Physics treats it with care, not because time is sacred, but because without its structure, nothing else would hold together. Ordinary experience offers quiet confirmation of everything physics suggests. Time is felt most strongly not when it moves smoothly, but when it resists manipulation. Waiting stretches moments. Urgency compresses them. Memory collapses years into images. Anticipation pulls attention forward. Yet none of these experiences allow reversal. No matter how vividly a moment is recalled, it does not become present again. The past remains accessible only through records that exist now. Those records are physical. Neurons fire. Synapses change strength. Photographs fade. Books age. Digital files degrade unless maintained. Memory is not a window into earlier time. It is a reconstruction built from present traces. This aligns precisely with how physics treats the past. The past survives only as information carried forward. There is no storage vault where moments remain intact. This physicality of memory exposes a deeper link. Conscious experience depends on irreversible processes. Neural activity consumes energy, produces heat, and increases entropy. Awareness itself unfolds in one direction because the mechanisms that support it do. Any scenario involving backward time travel would require consciousness to operate under reversed thermodynamic conditions, something no known biology or physics permits. Identity follows the same rule. A person persists because biological processes maintain structure across time. Cells repair damage. DNA replicates. Metabolism balances decay. These processes assume forward time. Reversing them would not restore a younger self. It would dismantle the system that defines the self in the first place. this insight dissolves a common misconception. Time travel is often imagined as relocation without transformation. Physics offers no such separation. Moving through time means participating in the processes that define time. Those processes do not support detachment. Even language reflects this constraint. Verbs encode tense because action unfolds. Grammar mirrors causality. Cause precedes effect. Description follows occurrence. Communication itself depends on time ordering. A message must be sent before it is received. Information theory formalizes this intuition. Communication channels require temporal direction to function. At microscopic scales, physics allows brief ambiguity. Quantum fluctuations blur sequences. Virtual particles appear and vanish. Yet these effects never accumulate into macroscopic reversals. They average out, leaving a clear arrow intact. The universe tolerates uncertainty locally while enforcing order globally. This pattern suggests that time's direction is scale-dependent, but outcome-consistent. Small systems flirt with reversibility. Large systems lock into irreversibility. Time travel to the past would require coordinating reversibility across all relevant scales simultaneously. No known process allows that alignment. Consider energy flow. Energy gradients drive change. Heat flows from hot to cold. Work extracts order from gradients. Reversing time would require reversing all gradients at once. Local reversal without global reversal fails immediately. The environment overwhelms the attempt. This environmental dominance is crucial. No system exists in isolation. Even the most carefully shielded experiment interacts weakly with surroundings. These interactions accumulate. They entangle the system's state with the rest of the universe. Time's arrow is reinforced by connection. The more connected a system becomes, the less reversible it is. Connection is everywhere. Light from distant stars strikes Earth. Cosmic rays pass through bodies. Gravitational fields extend without barrier. The universe is not a collection of sealed compartments. It is a web. Time flows through that web in one consistent direction. Attempts to imagine loopholes often rely on perfect isolation or control. Physics never observes either. Control is always approximate. Isolation is always partial. These limitations are not technological. They are fundamental consequences of how forces propagate. The speed of light plays a central role here. It limits how quickly information spreads. This limit structures causality. Events influence only those within their future light cones. Time travel to the past would require influence outside this structure. No experiment has ever observed such influence. Relativity does allow time ordering to vary between observers for events that cannot causally affect each other. This does not permit contradiction. It simply reflects the geometry of space-time. Causal structure remains intact. No observer sees an effect occur before its cause within their own frame. This preservation of local causality underpins all physical law. Without it, predictions fail. Experiments lose meaning. Science itself becomes impossible. The universe's apparent refusal to permit backward causation is therefore not incidental. It is foundational. The fascination with time travel persists because it exposes this foundation by contrast. Imagining its violation reveals how much depends on temporal order. Stability, memory, identity, communication, prediction all rely on it. Time, then, is not merely what clocks measure. It is the condition that allows structure to persist. Physics does not treat it as sacred. It treats it as necessary. When science says that time travel to the future is possible, it does so because that possibility preserves necessity. When it hesitates about the past, it does so because necessity breaks down. This distinction is not emotional, it is structural. It emerges independently from relativity, thermodynamics, quantum mechanics, information theory, and cosmology. Different languages, same conclusion. What remains unresolved is not whether time travel to the past will become practical. It is whether our understanding of time is complete. New theories may deepen insight into why time behaves as it does. They may reveal subtler constraints or unexpected connections. None so far loosen the arrow. As understanding grows, the mystery shifts. Time is no longer puzzling because it flows forward. It is puzzling because it flows forward while remaining flexible. It stretches without snapping. It differs without fragmenting. It binds without freezing. That balance is rare in nature. It suggests careful structure rather than accident. Physics continues to uncover that structure piece by piece, not by chasing fantasies, but by asking precise questions and following evidence. Time travel remains one such question. It endures not as a promise, but as a probe. By pressing against its limits, science clarifies what time is and why it behaves the way it does. Within that clarification, a quieter wonder appears. The universe does not allow revision, but it allows becoming. It does not permit return, but it permits transformation. Everything that exists participates in this forward unfolding, from particles to galaxies to thought itself. Time is the thread that holds those changes together, not a path to escape, but the medium through which all structure arises and persists. Physics also learns about time by studying what cannot be undone. Certain processes leave signatures so persistent that reversing them would require rewriting the universe at large. Nuclear reactions are one example. When a star fuses hydrogen into heavier elements, the released energy escapes as radiation, neutrinos, and motion. That energy disperses into space, altering countless systems. Even if the original star could be reconstructed, the energy it released would not spontaneously return. Time's arrow is etched into stellar history. Radioactive decay provides another window. An unstable nucleus transforms into a more stable one at a rate that can be predicted statistically, but not reversed. The decay products carry away energy and momentum. No known interaction recombines them into the original nucleus without external input, and that input always comes from processes that themselves move forward in time. Decay clocks do not run backward. They define durations across geology, archaeology, and cosmology. The same irreversibility appears in chemistry. Reactions proceed toward equilibrium. Bonds break and form according to energy landscapes shaped by temperature and environment. While some reactions are reversible under controlled conditions, the system as a whole moves toward states with greater entropy. Reversing every reaction simultaneously would require reversing every exchange of energy with the surroundings. The surroundings, in turn, would need to reverse their exchanges with everything else. The chain extends without limit. This interconnectedness matters. No physical process is isolated. Even deep space is filled with radiation, fields, and particles. Every system leaks information outward. Time's direction is reinforced by leakage. Once information escapes, it cannot be retrieved completely. The universe does not forget, but it does not keep records in a retrievable form. This view reframes time not as a line, but as a process of continual imprinting. Each moment leaves marks on the next. Those marks accumulate. The present carries traces of the past precisely because the past cannot be revisited. If it could, traces would be unnecessary. Memory would be redundant. Memory exists because time does not loop. Physics and biology converge here. Organisms that record their past gain predictive power. They adapt. They survive. Evolution exploits time's direction. A universe with unrestricted time reversal would undermine selection itself. Cause and effect would blur. Advantage would lose meaning. Selection operates far beyond biology. Physical systems also settle into stable configurations through processes that assume irreversibility. Galaxies form as matter collapses and radiates energy. Planetary systems emerge as disks, shed angular momentum. Structures arise because dissipation occurs. Dissipation is time-directed. It cannot be undone without external input that itself dissipates energy elsewhere. The emergence of structure therefore depends on time having a direction. This is not philosophical preference. It is mechanical necessity. Without dissipation, nothing organizes. Without organization, nothing persists. Seen through this lens, time travel to the past would not merely be unusual. It would be destabilizing. It would inject ambiguity into processes that rely on accumulation. Physics appears arranged to prevent that ambiguity from taking hold. This prevention is subtle. No single equation bans time reversal. Instead, the universe's initial conditions bias outcomes so strongly that reversal becomes inaccessible. Low entropy at the beginning creates an enormous gradient. Everything flows downhill from there. Climbing back up would require a miracle of coordination. Coordination is the recurring obstacle. Every attempt to imagine backward time travel demands perfect alignment across countless degrees of freedom. Slight misalignment produces runaway effects. Stability vanishes. Physics does not reward perfection. It rewards robustness. Robustness is what makes time dilation viable. Differences in rate can accumulate without destabilizing systems. Two clocks diverge slightly. The universe absorbs this easily. Causality remains local. Order persists. Backward influence lacks robustness. Small deviations amplify. Feedback loops grow. Predictions collapse. The universe appears to avoid such regimes not by prohibition, but by never settling into them. Even theoretical constructs that allow time loops often rely on idealizations that strip away noise, interaction, and complexity. When these features are restored, the loops dissolve. Reality intrudes. Noise is not a flaw. It is a feature of physical systems. Quantum fluctuations, thermal motion, environmental interaction are unavoidable. Any realistic scenario must accommodate them. Time reversal demands their elimination. Physics offers no path to that elimination. This insight connects time to uncertainty. The uncertainty principle limits how precisely certain quantities can be known simultaneously. That limit is not technological, it is fundamental. Perfect control over initial conditions is impossible. Without perfect control, reversal fails. The impossibility of perfect control reinforces time's arrow. The universe does not allow exact repetition. Every moment differs slightly from the last. These differences accumulate. History diverges irreversibly. From this perspective, time travel stories invert reality. They imagine a universe where control is absolute and noise absent. Physics reveals the opposite. Noise is intrinsic. Control is limited. Order emerges despite this, not because of its absence. The emergence of order under constraint is one of the universe's most remarkable features. Time's direction makes that emergence possible. It channels randomness into structure. This channeling is visible in the cosmic microwave background. Tiny fluctuations in the early universe grew into galaxies and clusters. Those fluctuations were random. Their growth followed deterministic laws. Time carried them forward into complexity. Reversing that growth would require erasing structure at every scale. Erasure is harder than creation. Creation exploits gradients. Erasure must overcome them. Time travel to the past would require systematic erasure of structure while preserving coherence. Physics does not provide such a mechanism. The more deeply time is examined, the more it appears woven into the universe's capacity to exist coherently. It orders events so that structures can form, persist, and interact predictably. It allows novelty without contradiction. Time travel to the future respects this ordering. It changes perspective without altering sequence. It allows observers to experience less time relative to others, but it does not reorder events along their own path. Backward travel threatens ordering itself. It would allow effects without causes, records without origins, memories without formation. Physics treats these not as curiosities, but as breakdowns. The distinction becomes clearer with each layer added. Geometry allows flexibility. Thermodynamics imposes direction. Information theory locks in records. Quantum mechanics enforces limits on control. Cosmology sets initial conditions. Together, they define time's behavior. No single pillar stands alone. Remove one, and the structure weakens. Time travel to the past would require removing several simultaneously. That convergence has not appeared in any credible theory. The question remains open in the narrowest mathematical sense. Equations can be written, solutions can be explored, but physical realization requires more than mathematical permission. It requires stability, consistency, and compatibility with everything else we know. So far, those requirements align against reversal, not as a dogma, but as an emergent pattern. Time, as science reveals it, is not a sequence of interchangeable moments. It is a cumulative process. Each moment inherits the consequences of the last. That inheritance cannot be revoked without unraveling the chain. Understanding this does not strip time of mystery. It relocates mystery. The wonder lies not in escape from time, but in how time supports complexity, memory, and meaning without collapsing into chaos. The universe permits change, but it insists on accountability. Every effect has a cause. Every record has an origin. Time enforces that accounting quietly, relentlessly. Within that enforcement, existence unfolds. Stars burn, minds think, histories accumulate. All of it happens because time moves forward and does not look back. Science continues to refine this picture, not to close curiosity, but to deepen understanding. Time travel remains a compelling question because it presses against the deepest constraints. By answering it carefully, physics reveals the architecture that holds reality together. A deeper implication appears when time is examined through the lens of prediction. Physics is, at its core, a predictive framework. Given present conditions, it forecasts future behavior. This ability depends entirely on time having a consistent direction. Predictions point forward because causes propagate forward. The success of physics across centuries is evidence that this directional structure is reliable. If backward time travel were physically accessible, prediction would lose meaning. A future event could alter present conditions after a prediction had been made, invalidating the framework that produced it. The universe would become epistemically unstable. Knowledge would no longer accumulate. Science would be impossible not because humans failed, but because reality itself would refuse consistency. This observation is not philosophical speculation. It is a consequence of how physical law functions. Laws are time-local. They connect neighboring moments. They do not reach arbitrarily across time. This locality ensures that small uncertainties remain small as systems evolve. Backward influence would break this containment, allowing distant events to interfere with local dynamics. Containment is essential for stability. Without it, systems would experience uncontrolled feedback. Small fluctuations could grow without bound. The universe would not merely be strange, it would be uninhabitable. These considerations explain why time travel questions are often addressed indirectly. Instead of asking whether a machine could be built, physicists ask whether a universe that allows such machines could exist stably. Every answer points toward the same conclusion. Stability demands temporal order. This demand does not come from conservatism. Physics embraces radical ideas when evidence supports them. Relativity itself overturned centuries of intuition. Quantum mechanics shattered classical determinism. The resistance to backward time travel is not ideological. It is structural. Structure becomes visible again when examining how physical systems relax. After disturbance, systems return to equilibrium. This relaxation dissipates energy and erases information about precise initial states. Relaxation is time-directed. It allows systems to remain bounded. Without it, disturbances would accumulate. Relaxation underlies everything from climate stability to atomic structure. It is how systems avoid runaway behavior. Time reversal would invert relaxation into amplification. Disturbances would grow rather than fade. Stability would vanish. Amplification without bound is a warning sign in physics. Whenever equations predict it, physicists look for missing constraints or incorrect assumptions. The appearance of amplification in time loop models suggests that something essential has been overlooked. The universe seems to enforce constraints that prevent such scenarios from becoming real. Another constraint arises from energy conditions in relativity. These conditions limit how energy and momentum can behave. They are not arbitrary. They encode empirical facts about matter and fields. Many time travel proposals require violations of these conditions. Such violations have not been observed and may be impossible in stable configurations. Quantum effects allow temporary, local violations of some energy conditions, but they do so under strict limits. These violations are fleeting and balanced. Scaling them up leads to instability. Once again, physics allows flirtation, not commitment. The consistency of these outcomes across independent approaches is striking. Different theories, different tools, same barrier. Time reversal is mathematically imaginable, but physically unachievable under known laws. This convergence gives weight to the idea that time's arrow is emergent but robust. It arises from initial conditions, interactions, and statistical behavior. Yet once established, it becomes extraordinarily difficult to disrupt. Robustness is a recurring theme. Physical laws are tolerant of noise. They accommodate imperfection. Time's direction survives despite fluctuations, disturbances, and uncertainty. That survival suggests it is not a fragile artifact, but a deeply rooted feature. Understanding this feature reframes the emotional appeal of time travel. The desire to revisit the past often reflects a wish to undo loss or error. Physics responds not with indifference, but with explanation. Undoing is incompatible with how reality maintains coherence. This does not render the past irrelevant. The past shapes the present through records, structures, and constraints. It remains active through its consequences. But it cannot be accessed directly because it no longer exists as a state. It exists only as influence. Influence is one way. Past influences present. Present does not influence past. This asymmetry is not moral. It is mechanical. Even in quantum mechanics, where measurement choices affect outcomes, the effect is confined within causal structure. No choice alters an already recorded event. Retroactive descriptions do not imply retroactive causation. The mathematics preserves consistency. Consistency emerges again as the central value. Physics tolerates uncertainty, randomness, and complexity. It does not tolerate contradiction. Time travel to the past invites contradiction at multiple levels. The universe responds by making such scenarios unattainable. This response is not conscious. It is encoded in the behavior of fields, particles, and space-time. The universe does not decide. It behaves. As theories evolve, the language used to describe time may change. Time may become emergent, relational, or informational. Yet in every formulation that successfully describes reality, a directional ordering remains. Something plays the role of time, even if it is not named. As such, that role is indispensable. It orders change. It anchors causality. It allows memory. It supports identity. It enables explanation. Time travel to the future respects that role. It alters experience without undermining structure. Time travel to the past attempts to bypass the role entirely. Physics responds by closing ranks around structure. The cumulative picture that emerges is coherent and restrained. Time is neither a simple line nor a freely navigable dimension. It is a dynamic ordering principle shaped by motion, gravity, entropy, and information. It can be stretched and skewed, but not inverted. This picture continues to sharpen as experiments grow more precise and theories more unified. Each refinement reduces ambiguity, not by narrowing imagination, but by clarifying constraint. Constraint in physics is not limitation. It is definition. It tells us what kind of universe we inhabit. A universe that allows complexity to persist, knowledge to accumulate, and history to have weight. Within such a universe, time travel remains a question worth asking, not because it promises escape, but because it reveals why escape is not possible without collapse. Time, as science describes it, is the quiet custodian of coherence. It does not announce itself. It simply ensures that what happens makes sense. That sense-making is what allows stars to burn steadily, atoms to bond reliably, and minds to reflect it all. It is what allows the universe to be more than noise. Understanding time travel, then, is inseparable from understanding why there is order rather than confusion. Physics approaches this understanding patiently, tracing the threads that bind events together. Those threads all run in one direction. Another constraint becomes visible when time is examined through symmetry and its breaking. Many fundamental equations of physics look almost indifferent to whether time runs forward or backward. Replace t with minus t, and the mathematics often remains valid. At first glance, this seems to invite reversal. Yet the universe does not behave according to equations alone. It behaves according to specific solutions, shaped by boundary conditions and initial states. The early universe provided one such boundary. Observations of the cosmic microwave background show an astonishing degree of uniformity with tiny irregularities. That uniformity corresponds to an extremely low entropy state. From that state onward, entropy increased. This single fact does enormous work. It establishes a direction not because the laws demand it, but because the starting point selected it. Once selected, the direction propagates everywhere. Because of this, time travel to the past would not be a local maneuver. It would conflict with a global condition that has shaped the entire universe. Every structure that exists is downstream of that initial asymmetry. Galaxies, stars, chemistry, biology, memory, all owe their existence to the gradient established at the beginning. Reversing time locally would mean fighting a universe-scale tide. That tide expresses itself subtly. Consider radiation. Light carries energy away from sources and spreads it across space. Once emitted, photons travel outward, rarely returning. The night sky is dark because radiation dilutes. Reversing time would require radiation to reconverge spontaneously, reconstructing its sources. Physics allows this in principle for a few particles. It does not permit it for the cosmos. The same applies to gravitational waves. When massive objects accelerate, they send ripples through space-time that propagate outward forever. Those ripples carry away energy and information. They are records of events that cannot be erased. Time's arrow is written into space-time itself through these waves. Undoing them would require space-time to ring backward. Space-time does not appear to support such ringing. Once distorted, it relaxes. Disturbances fade. Geometry settles. Relaxation again enforces direction. Another perspective emerges from computational physics. The universe can be viewed as performing a vast computation, evolving its state according to local rules. Computation depends on irreversible operations. Bits are erased. Heat is produced. Landauer's principle links information erasure directly to energy dissipation. Any process that erases information must increase entropy. Time travel to the past would require uncomputing the universe, undoing erased bits without paying the thermodynamic cost. No physical system has ever demonstrated such uncomputation at macroscopic scales. Computation proceeds forward because erasure accumulates. This computational framing clarifies why information is so central. The past is not merely earlier time, it is earlier information. Once information has been overwritten, scattered, or erased, it cannot be recovered without external input that itself produces new erasure elsewhere. The ledger never balances backward. Ledger keeping is not metaphorical. Physics tracks conserved quantities meticulously. Energy, momentum, charge all obey strict accounting rules. Time travel to the past would complicate this accounting severely. Duplicated objects would duplicate conserved quantities. Removing them would require unexplained sinks. The universe shows no sign of such bookkeeping anomalies. Even speculative fixes struggle. Self-consistency conditions attempt to ensure no net duplication occurs. Yet enforcing them requires constraints so tight that free choice disappears. Events become locked. History becomes self-enforcing. The very notion of intervention collapses. At that point, time travel ceases to resemble travel. It becomes a reinterpretation of causation. The traveler was always part of the past. Nothing was changed. The appeal dissolves. Quantum mechanics does not rescue the situation. While quantum theory allows superpositions and indeterminacy, it does not allow contradictions. Measurement outcomes remain consistent within each history. Decoherence prevents macroscopic superpositions from persisting. The classical world emerges with a clear arrow. Some proposals invoke post-selection to simulate backward influence. These experiments condition outcomes on future measurements, creating correlations that look retroactive. Yet no usable signal travels backward. No cause precedes itself. The appearance of retrocausality dissolves under closer inspection. The deeper reason lies in probability. Quantum probabilities are normalized. They sum to 1. Allowing backward causation would disrupt normalization. Outcomes could amplify or suppress each other unpredictably. Consistent probability assignment would fail. Physics relies on probability remaining well-defined. Another quiet constraint comes from locality. Physical influence diminishes with distance and time. Fields weaken. Correlations decay. This decay ensures that distant past events do not exert arbitrary control over the present. Time travel would invert this, allowing remote events to exert disproportionate influence. The universe seems carefully arranged to prevent such inversions. Influence flows outward, not inward. Effects spread, they do not concentrate. This spreading underlies both entropy and causality. It is the same principle expressed in different language. Looking outward, astrophysical observations reinforce this picture relentlessly. Supernovae explode, and their remnants expand. Galaxies merge, and their debris disperses. Black holes accrete matter, and energy escapes as radiation. Everywhere, processes unfold with direction. Nowhere is there evidence of large-scale convergence of effects back into causes. No star unburns, no galaxy uncollides, no radiation refocuses to recreate its source. The absence is not subtle, it is universal. This universality matters. If backward time travel were possible even rarely, the universe would show scars. Anomalies would appear. Histories would overlap. Observations would conflict. Instead, observations align across independent measurements and methods. History agrees with itself. Agreement is fragile. It requires coordination across vast scales. That coordination exists. Time's arrow enforces it. Even speculative cosmologies that allow exotic behavior tend to preserve this arrow within each causal domain. Bubble universes, multiverses, and branching histories all maintain local order. They multiply futures, not pasts. They preserve causality within each branch. This preservation suggests that time's direction is not an optional feature layered atop physics. It is embedded in the logic that allows any description at all. As understanding deepens, time travel becomes less a question about possibility and more a question about meaning. What would it mean for history to be revisable? What would it mean for records to lose authority? What would it mean for identity to fragment? Physics answers indirectly. A universe that allowed such flexibility would not support stable structures long enough for questions to be asked. The fact that questions exist is evidence that constraints hold. This is not circular reasoning. It is inference from consistency. The universe behaves in ways that permit cumulative knowledge. That behavior depends on time's arrow. Future-directed time travel remains a special case that fits within this framework. It does not revise history. It merely samples it unevenly. An observer experiences less time while the universe advances. No contradiction arises. The ledger balances. Backward travel would unbalance the ledger. Every attempt to imagine it reveals hidden dependencies. Remove time's direction, and everything else trembles. The fascination endures because the idea presses on something deeply human. Regret, curiosity, longing all point backward. Physics responds by explaining why backward-pointing desire cannot become backward-pointing causation. This explanation does not trivialize desire. It contextualizes it. The universe offers growth, not revision. It offers learning, not erasure. Time enforces this distinction quietly. By studying time travel, science clarifies this enforcement, not as a rule imposed from outside, but as an emergent property of laws, conditions, and interactions woven together. Time is not simply what passes. It is what preserves coherence as change accumulates. And within that preservation, everything that exists finds room to unfold. Another way the structure of time reveals itself is through the concept of horizons. Horizons are limits beyond which information cannot reach an observer. Event horizons surround black holes. Cosmological horizons surround the observable universe. These boundaries are not walls in space. They are boundaries in time and causality. They define what can influence what. A horizon exists because time moves forward locally, and information propagates at a finite speed. Light emitted beyond a certain distance will never arrive, not because space blocks it, but because the universe expands and time advances in such a way that the signal can never catch up. The past beyond that horizon is not hidden somewhere. It is simply unreachable. This matters because time travel to the past would require violating horizon structure. Information from beyond a causal boundary would need to appear where it does not belong. Physics has never observed such boundary violations. Horizons remain intact across every scale examined. Black hole horizons are especially instructive. Once crossed, all future paths lead inward. No signal escapes. This is not because space pulls harder, but because time itself tilts inward. Every possible future points toward the center. Even here, where intuition breaks down, time remains directional. There is no path that leads outward once the horizon is crossed. Attempts to imagine using black holes as time machines confront this immediately. The very geometry that distorts time so dramatically also locks causality in place. The deeper the distortion, the stricter the ordering becomes. Cosmological horizons enforce a similar discipline. The observable universe has a finite age. Light has traveled only so far. Beyond that distance, events exist that will never influence us. Not now, not ever. Time does not grant access simply because something exists. Access depends on causal structure. This limitation exposes another misconception. Time travel is often imagined as access without interaction, as though one could arrive at a moment without belonging to its causal network. Physics does not recognize such detachment. To exist anywhere is to interact. To interact is to alter causal relationships. Alteration propagates forward. Propagation forward is the key. Every interaction sends influences outward in time. There is no known mechanism for influence to propagate backward without destabilizing everything it touches. This becomes even clearer when examining feedback systems. In engineering and biology, feedback can stabilize or destabilize a system depending on its timing. Delayed feedback can produce oscillation. Immediate feedback can dampen fluctuations. Feedback that arrives before the input would create runaway behavior. Systems would amplify noise uncontrollably. Physics treats backward causation as a form of anticipatory feedback. Such feedback is catastrophically unstable. Small fluctuations would explode. Order would dissolve. The universe we observe does not exhibit such behavior. Stability, once again, emerges as the silent arbiter. the universe appears to favor configurations that dampen disturbances rather than amplify them. Time's arrow supports damping. Reversal undermines it. The same principle governs learning. Learning systems adjust behavior based on past input. They rely on stored information. If future outcomes could alter past inputs, learning would fail. Adaptation would lose coherence. Intelligence itself depends on temporal order. This dependence is not restricted to biology. Machine learning systems, physical control systems, and natural processes all rely on feedback loops that assume time flows forward. The success of such systems across domains reflects a universe aligned with this assumption. Even randomness depends on time's direction. Random events are defined by unpredictability from present information. If future information could influence present randomness, probability would lose meaning. Randomness would become retroactively determined. Physics avoids this by preserving causal independence. At the deepest levels, quantum theory enforces this through the no signaling principle. Entanglement produces correlations, not control. Measurement choices do not transmit information backward. Correlations appear only when results are compared later in the forward flow of time. The insistence on no signaling backward is not arbitrary. It preserves probability consistency. It ensures that outcomes remain locally random. It protects the statistical structure of reality. Every layer examined points toward the same architecture. Time is flexible in rate, strict in order. It allows variation without contradiction. It enables complexity without collapse. This architecture explains why time travel stories require special pleading. They isolate characters from consequences. They assume perfect control, perfect isolation, perfect knowledge. Physics recognizes none of these as attainable. Imperfection is not a flaw. It is fundamental. Fundamental imperfection does not produce chaos because time channels it. Uncertainty spreads, but it spreads forward. That spreading smooths rather than disrupts. It allows systems to settle. Settling is essential. Without it, nothing would persist long enough to matter. Time provides settling by allowing disturbances to dissipate. Dissipation is irreversible. Energy spreads. Information disperses. Patterns degrade unless maintained. Maintenance itself consumes energy and produces entropy. The cycle never closes backward. This irreversibility is often framed as loss. In physics, it is structure. It is the reason there is an arrow at all. Without it, the universe would be static or chaotic. Neither supports complexity. Time travel to the past would interrupt dissipation. It would reconcentrate energy and information without cost. Physics offers no such free operation. Every reconcentration observed requires greater dispersion elsewhere. The ledger remains unbalanced backward. Forward, it balances naturally. This asymmetry has nothing to do with human desire or narrative preference. It is written into the behavior of fields and particles. It is enforced by statistics and geometry. It emerges from initial conditions and propagates through interaction. When science speaks about time travel, it is really speaking about whether this asymmetry can be bypassed. Every credible answer so far says no. The answer is not shouted. It is inferred. It emerges from the quiet consistency of observation and theory, aligning again and again. Time's arrow is not a rule added on top of physics. It is what allows physics to function. Within that allowance, extraordinary things happen. Clocks diverge. Aging differs. Gravity slows time. Motion reshapes duration. These effects are real, measurable, and profound. They remind us that time is not trivial. It is dynamic. It responds to mass and motion. It weaves space into a single fabric. But even as it bends, it does not break. Even as it stretches, it does not reverse. That restraint is not limitation. It is coherence. And coherence is what allows a universe to exist not just as motion, but as history. What finally comes into focus is that time is not simply a sequence of moments laid out like pages in a book. It is the mechanism by which the universe preserves consistency as change unfolds. Every process examined, from the smallest quantum interaction to the evolution of the cosmos, relies on this consistency. Time orders events so that causes generate effects, records form, structures persist, and knowledge accumulates. When science is asked about time traveling, it answers by revealing this ordering in ever finer detail. It shows how motion and gravity reshape the rate at which time is experienced without disrupting order. It shows how entropy and information flow lock history into place without freezing the future. It shows how causality threads through space-time, preventing contradiction while allowing richness and diversity of experience. The picture that emerges is neither permissive nor prohibitive in a simplistic way. It is selective. The universe allows paths into the future because those paths respect the architecture that holds everything together. It resists paths into the past because those paths would unravel that architecture at every level at once. This resistance is not a failure of imagination. It is a sign of depth. Time is not shallow enough to be stepped across freely. It is deep enough to support memory, identity, and meaning without collapsing under paradox. Seen clearly, time travel ceases to be a question about machines or destinations. It becomes a question about what kind of universe can exist coherently. The answer offered by physics is quiet and consistent. A universe that allows history to be rewritten would not remain stable long enough to host observers capable of asking the question. The wonder, then, is not that time travel to the past appears unreachable. The wonder is that time is flexible at all, that it bends under motion, slows under gravity, diverges between observers, and yet remains ordered enough to allow stars to shine, atoms to bond, and minds to reflect. Time, as science understands it, is not an obstacle placed in our way. It is the condition that allows anything to happen with continuity. It does not grant revision, but it grants becoming. It does not permit return, but it permits growth. In that light, the deepest answer science gives about time traveling is not a prohibition, but a revelation. Time is not a corridor to wander. It is the structure that lets the universe have a story at all. If this quiet journey brought you a moment of calm, a gentle like or a soft tap on subscribe truly helps keep this calm corner of the universe glowing. And tell me, where in the world are you listening from tonight? Rest well until our next quiet journey.